so this is a horizontal momentum of this. So in the end, it's 0. So basically, the moment change is this direction, and moment change is this direction. But you need to sum up all the moment change. So there are some kind of you need to sum up all the moment change. So you need to consider the density here and the density here, and in the end, the total force is in this direction.
Not very obvious.
So the particles will move to the hot area?
Yes.
Using this model?
Yes. So, okay.
The original momentum is killed by the boundary. So the boundary gives the force to the empty direction.
Yes, but and the net force is in this direction. So maybe we can come back to this later. The problem we consider is we consider two infinite plates and put it in minus 1/2 and 1/2, and we consider we model the gas by linearized Boltzmann equation in between, and on the boundary we use the diffuse refraction boundary condition, and we consider the temperature gradient on the boundary is say epsilon times x2, and epsilon is the temperature gradient. Okay, so that is, and here this is stationary Boltzmann equation, but this kappa is called Knudsen number. It is the ratio between the mean free path and the reference length. And L is a linearized collision operator. So linear, okay, maybe I'll skip here. So this is a diffuse refraction boundary condition, linearized diffuse refraction boundary condition. And the result joint work with I-Kun Chen and Taiping, Liu, and Sonnen in 2007, we proved first for large enough kappa, there exists a bounded solution. And this solution do not have pressure gradient in x2 direction, but the flow velocity is bounded below and above by log k. So that's what we proved in 2007. And in 2010, Takata and Funagane, they have a numerical result on a similar problem, and furthermore, they find a asymptotic formula for the total flux. Here we only have the upper bound and lower bound and upper bound.
Well, we must go back to the previous page then, because we have no feeling of kappa.
Here?
Different, yeah. So, what is the meaning of kappa?
Kappa is mean free path, the ratio between mean free path and reference length. So
what is the reference length then?
Reference length, it depends on the problem. For example, if you are interested in set up in the tube with the length L, and then the mean free path is L naught, then the kappa should be the reference length the length you are interested in.
Okay. And here you have two boundaries.
Yes. So, but it can be other thing. But this is, for example, if you have two boundaries, then it's the distance between two boundaries is reference length. And L naught is the mean free path. It is distance in average you will hit another particle.
Like a large, when kappa is very large, this is very dilute.
Yes, yes. So this phenomena happened in a very dilute gas.
So the collision with boundary is much more important than the collision between particles.
Yes, yes. Thank you. I think that's a good point. And in 2010, we have another paper. First, we prove a better kind of solution. It's Gaussian-like. It has very thin tail. And then the other thing is, originally we have only upper bound and lower bound for the flow velocity. Now we are able to write down the asymptotic formula for the flow velocity. But our goal is to prove the macroscopic quantity has x log x behavior like this. However, this asymptotic formula is not enough to show this because this will tend to 0 when x1 tends to -1/2, but then it is dominated by the error term. So eventually we prove the derivative of the flow velocity in x1 direction and write down its asymptotic formula as this. So in this case we see the derivative of flow velocity will diverge like log function when x is close to the boundary. So I think this is the first analysis on this phenomena for the linearized Boltzmann equation. But this raises issues so far I cannot solve. That is, as we know that we prove that this quantity, the flow velocity, the derivative of flow velocity in x1 direction is diverged like log when the x1 is close to 1/2. But in the kinetic theory, the shear stress can be calculated like this. And in this case, we can calculate it is bounded. But remember, in fluid dynamics, we usually have for a Newtonian fluid, there is one condition, that is the stress is proportional to the gradient of the flow velocity. So for example, if you have a flow like this, and you put an imaginary plane here, and if this is x1 direction and this is x2 direction, then the force you experience is usually proportional to the this is Q2 to the gradient of velocity in this direction. So this is for Newtonian fluid. But here you can see this reaction cannot hold in this situation because the gradient of the flow velocity tends to infinity like log function, but the shear stress keep bounded. So here we can conclude that in this region, when it's very dilute and you consider linearized Boltzmann equation, the physics do not follow the Newtonian fluid.
By the way, your x1 goes to 1/2, this means right between the two planes, so what is it?
Yes, like x, this is 1/2 and this is -1/2. So it's near this boundary.
Why do you call it 1/2?
Uh,
Because you call the length L, so it's 1/2 L and plus minus 1/2 L.
but now, because we non-dimensionalize the whole problem, so L become 1, and it absorbed into the non-dimensional constant kappa.
So there's nothing particular on the minus 1/2?
So in the -1/2, it's symmetric situation. So it will tend to
So that's a symmetric.
yeah. So basically, this mu is a viscosity. So basically, in this region, for a very dilute gas, I don't know how to describe viscosity. So I just observed that the Newtonian, you cannot use the Newtonian fluid to describe the flow, but I don't know what is the right model for it.
Very dilute gas is not exactly a fluid. It's not only not exactly, it's not a fluid.
It's okay.
So, yeah.
So, okay.
You can say this, the gas still in a thermal equilibrium through the collision with boundary.
I think in this case, it's very far from the equilibrium. Yeah. So maybe that's maybe I should think through this again. But at least it's not fluid. Like
For this divergence, can we say near the boundary when maybe the boundary condition cannot hold it anymore, very close to the boundary?
The boundary condition here is diffuse refraction boundary condition. So
it's some kind of macroscopic boundary condition.
It's microscopic.
It's microscopic?
Microscopic
Okay.
boundary condition.
You can hold it even for very short distance to the boundary.
So basically, on this boundary, the condition is the flux is going, the particle going must go out, so the zero flux. The second is the particle going into the gas is in the form of Maxwellian, that is equilibrium with the temperature on the boundary. So there are only these two conditions, and our solutions satisfy these two conditions.
Now the second part is kind of thermal equilibrium.
But maybe, in fact, it's equilibrium with the boundary,
Yes,
but
yes.
not with the gas.
Yeah, yes.
So, okay, so maybe.
But the whole thing has experimental base, right? You mentioned earlier experiment, also the motivation for Maxwell.
Yes, I should say numerical experiment. So
It's always numerical.
always
So
nu-
Maxwell was numerical?
The thermal transpiration can be observed by just very simple experiment, but this phenomena is not easy to catch. The singularity on the boundary, because it's a very subtle singularity. It's singularity in the derivative, not in the function itself. But the numerically they report is they find this kind of singularity.
Well, as a physicist, I would like to see the experimental demonstration.
Yeah, but how do you measure the derivative in an experiment? I think it's a little not so easy. So okay, maybe I need to speed up a little bit. So in their work in 2010, they first proved the logarithmic singularity for the flow velocity for various kappa. in our work, we only prove the singularity for big kappa, but they can numerical prove show that this phenomena happen for various kappa, and then they find the microscopic velocity has singularity, as we showed before. And the third one is they conclude that the singularity in microscopic velocity in the singularity in the flow velocity is induced by the jump discontinuity on the boundary, and those are all numerical results, all numerical arguments. And to address the singularity in the microscopic velocity, we prove the following: the derivative of the flow of the velocity distribution function in respect to zeta1, has a asymptotic formula like this, and it behaves like log C1, log zeta1, when zeta1 is small. And this function can be written down exactly, explicitly, and I naught is zero order modified Bessel function of the first order. And for this result, we construct, because this is a precise problem, and we just construct the solution by iteration scheme, and the first or second term has a property we want, and we estimate the rest is dominated. It can be dominated. So that is the way we prove these two results. But in general, we want to prove a general theory for this. So in the end, maybe I need to rush. In the end, we prove that if linearized Boltzmann equation has a solution near the boundary, and the solution is in this functional space. That functional space means the velocity distribution function is weighted L2 in velocity, and this L2 norm is bounded. And the derivative of velocity distribution function is L2 for fixed x, and it is locally L2 in x. So why we choose this is because there is an existent result proved by three mathematicians in 1986, and their solution is in this space. So maybe I should rush up a little bit. So the main result is if f is inside the functional space we introduce and satisfy the stationary linearized Boltzmann equation, and the other condition is the velocity distribution function toward the gas region is Holder continuous for zeta1 between 0 and 1. Then for small enough x, the derivative of moments, this is an arbitrary moment with order alpha. Then we have a asymptotic formula for it, and it looks like log x times an integral and plus a constant. And what inside is only involve the collision operator on the boundary when x is equal to 0. So this theory shows give a necessary and sufficient condition for logarithmic singularity. That means the derivative of moments, or the derivative of macroscopic quantity, will have log singularity if and only if this is not zero. And this is only involve the collision term on the boundary. And now we do not. Now we know that from conservational point of view, we know that the flux of density, flow velocity, and temperature in zeta-1 direction is a constant with respect to x. But if we compare with the theory we have, if we take alpha 1 is not zero, then we prove that if alpha 1 is not zero, then this thing will be zero because it will have C1 alpha 1 in this function. So this will be zero. This will be bounded. We will not have log singularity, and these two facts are coincide. It's consistent. Sorry. So if we have a further condition, if we assume that the f is bounded for if the C1 is less than zero for at some point, then we can further simplify the situation into the symptomatic formula into this, like it will become log x times an integral plus an bounded term, and this integral is only involve the jump of the flow velocity, of the distribution velocity distribution function at zeta-1 equal to 0. So then this is consistent with Takata and Nagane's results. For this half-space problem, it's called Melnet problem if we consider the distribution is bounded when x is very big, and we call it Kramer problem when we allow it to grow linearly. And these two problems are solved by Bartels, Kefelish, and Nikolenko. For example, the Melnet problem, they have this result, and the functional space they have is like this. So if we restrict the functional space into the from 0 to L instead of to the whole space, then you will see this is the functional space we use in our theory. So basically, our theory can apply to this problem. So because due to the time, maybe we'll skip the sketch of the proof. And thank you.
Let's not jump to the conclusions, but jumping to the end. Okay, any questions? No questions. Anyway, it's pretty amazing that this Boltzmann equation title for us physicists can turn into all this mathematical notation. But still, questions. This is bridging the gap between physics and math, and this guy knows something about physics, so it's the person to ask.
Any questions?
If there is a physical meaning to choose the kind of the space of function like the how can I say that you define some sort of like a norm or something, the functional space in such a way that some integration is finite.
Oh, you mean?
Yes.
Let me try this. You mean this?
Yeah, or yeah. Or
Oh, okay.
like a deep line.
In fact, this assumption, with this assumption, they can solve the problem. So, and in fact, this has a physical meaning. Really has a physical meaning. That the linearized Boltzmann equation is like this, and the collision, linearized collision operator can be decomposed into two parts. And one is a multiplicative operator, one is the integral operator. And this means the collision has some damping effect in the linearized Boltzmann equation. And this is called collision frequency. And this collision frequency in our model is like this. So it's proportional to this. So basically, this kind of condition is related to the damping here, but it's a little too much to go into detail. But it's the damping helps, and the damping is of this order.
Thank you.
You are welcome.
Can you go back to the Maxwell page? So you mentioned Maxwell, so the page before that.
Okay. Okay.
So the page before, just before, the page.
Okay. Here.
So I'm curious that in Maxwell's time, I don't think there's any computers, so there's no computing data like what you're talking about. So were there physical situations such that Maxwell talked about this?
I think in that time, the kinetic theory is underdeveloped, but they have some assumption that okay, maybe I should answer again. What is it?
No, because this is where we can connect.
Mm-hmm. Yes.
Maxwell, of course, is the Maxwell for Maxwellian.
Mm-hmm.
So he discussed about diffuse reflection out of this consideration, but was this a theoretical development, or there was some data?
It's a theoretical development after an assumption, that is, they assume the equilibrium between those.
So a little bit like what you. Okay. So this is kind of the source of
yes.
his kinetic theory with boundary conditions.
Yes.
As a mathematical question.
Yes.
Okay.
But his assumption is that the solution, the distribution function is a Maxwellian distribution, but with the parameter as a function of space. So that's his assumption. That is, he has some pre-assumption on the shape of the distribution.
So Renfrew needs to find a way to measure velocity gradients of very dilute gas. To make okay, I think.
Jin Zhen can do this.
Yes?
Maybe Jin Zhen can do this.
Very dilute gas. But this does not mean low temperature. So I don't know what's the relevance of temperature here as a mathematical concept. Does high and low, what's the reference point for high and low? The scaleless meaning of temperature, just like the scaleless problem here. Anyway, I think the most fascinating thing is how math people do it. Right? So we asked more questions from the physics side. That's why you couldn't discuss your math. But that's probably why we asked those questions. Okay, so let's thank Professor Chen again.